Hi everyone. So this is from the Productive Cloud Innovations. So this is our first series coming out to you, Fallacies in the Cloud, Fallacies in Distributed System. And what do you think about it? And we have a great speaker for you, Mark Richards. So Mark, floor is with you.
Awesome. Thank you, Rohit. So, these fallacies are quite interesting. Back in 1994, Peter Deutsch and some other folks from Sun Microsystems coined the 8 fallacies of distributed computing. Now, a fallacy is something that we believe to be true, but it's exactly the opposite. It's not true. These are things that we tend to forget about when we start talking about distributed systems and distributed architecture. I thought this was a really cool podcast to do, Rohit, because most cloud-based implementations are in fact distributed architectures. And as developers, architects, designers, you name it, we tend to forget about these fallacies and we get bit by them. So some of these have quite a bit of significance. Well, all of them do in distributed computing, but especially within cloud-based infrastructures.
Nice. So, I know that this is a near and dear topic to me also, like, when we design an application. So I would love you to start with the first one in the list, like the network is the most reliable thing we got. So,
Yep. So let's start from the top. Fallacy number 1 of distributed computing is that the network is reliable, and in fact, it is not. Now, granted, networks are a little bit more reliable than they were in 1994 when Peter Deutsch and folks from Sun coined these. But the problem is we make the assumption that networks are reliable, and we can have, Rohit, a perfectly healthy service in any kind of environment, cloud or otherwise. And the problem is we can't get to that service, or worse, Rohit, we actually get to that service to, let's say, place a trade for 1,000 shares of a buy for Apple. And the problem is that trade gets placed and that service is trying to give me a confirmation number, and it can't because of the network. And so we start to end up with all these reliability problems because the network, Rohit, is not reliable.
Yeah, absolutely. I mean, one of the things which I always think about is, like, what happened to those request and abandoned request and responses. So how
Yeah.
to handle that?
Well, so Rohit, this is what's given rise to a pattern called the circuit breaker pattern. Circuit breakers, so generally what we do in most distributed systems, including cloud-based infrastructures, well, actually, we're going to get into the other 7, but especially cloud-based. You'll see where some of these really play into how significant they are in cloud. But the point is that usually we have some sort of timeout value that we try to set. And the problem is this can vary. It's a configuration parameter we never look at. Boy, we can go ad nauseum on several podcasts about how to self-configure those. But my point being that this has given rise to a pattern called a circuit breaker. As a matter of fact, Rohit, Michael Nygaard, in his first release or first edition of Release It, actually introduced this pattern. Where, in fact, Kubernetes now, for example, a lot of cloud-based orchestrators now have these circuit breakers built in, so they're constantly monitoring pinging a service. Well, there's many different kinds of circuit breakers, but my point is they're constantly checking to see if the service is responsive, and usually that's based on real-time metrics, and it's analyzing these using standard deviation analysis. And if it starts to see that there's a climb in the response rates, it will deem that service unhealthy. It will stop it and start up another service. And so these circuit breakers are really the pattern within the context of this very first fallacy, which in fact the networks are not reliable, and we may be sitting there waiting and waiting and waiting for a response.
Yeah, I mean, one thing which I always say, like, even if you're not using circuit breaker, like, exponential backoff, for example, is like is I think circuit breaker is using internally, but people need to know it. What I see, what's your thought on that? Like, you should not retry again and again after some time. Like, you need to do exponentially back yourself off. You have any thoughts on that?
There's, I do. There's a lot of different implementations of circuit breaker. As a matter of fact, on my website, developer2architect.com, and that's a T-O, developer2architect.com, I have a bunch of lessons. And as a matter of fact, I've got a lesson on the circuit breaker pattern. You can also Google it and find a great article by Martin Fowler on the circuit breaker. But to answer kind of your question, I think it's twofold, Rohit. It's knowledge that a circuit breaker exists. Actually, it should say it's threefold.
Yeah.
Knowledge that the circuit breaker exists, number one. Number two, the various implementations of a circuit breaker. And to see what sort of orchestration tool you're using, does it actually support a circuit breaker? There are, Rohit, three types of circuit breakers, and this is kind of important to know when you're actually utilizing one or selecting one. The first is just a simple ping. You know, it just does a really quick millisecond ping to the service, and it basically says, are you there? Are you there? Are you there? Now, this kind of circuit breaker is really just used for availability, but not responsiveness. You see, because that trade, let's say that trade placement service, we just did that example of, Rohit. That trade placement service may be alive and well. And that circuit breaker says, oh yeah, you're there. Are you there? Yep. Are you there yet? Yet the trade or the place trade endpoint is not working. It's not functional because of some sort of deadlock or some sort of resource problem, some sort of threat allocation. And so my point is, these are not good circuit breakers to use when you're analyzing kind of the aspect that we're talking about, which is I need a response from you. So those are usually done for more availability. However, there's two other kinds of circuit breakers. The first utilizes something called synthetic transactions, where you actually put a fake transaction through periodically. Let's say a trade for a buy for QSIP 9999999, for example, which doesn't exist, or maybe a telephone company switching, which is using 8675309 as the number. That's a little joke. That's Jenny's number. But synthetic transactions also have their share of problems because it's really testing, Rohit, one particular path through that service. And the problem is it's not really exercising other maybe threads, connections, other types of processing or validations that may actually be stuck. So the third type, which are the best circuit breakers, by the way, are real-time monitoring, where the circuit breaker is constantly monitoring real-time transactions. And it has something called a half-open state. You see, if the circuit breaker is closed, what that means is that, like the circuit breaker in your house, electricity is flowing straight through. And so that's perfect. Now, when that circuit breaker detects a problem in responsiveness based on some sort of trend analysis, like I said, usually with standard deviation, that trips it open. And what that means is that no requests can get through. However, the problem is with real-time monitoring, so I'm going to move my hand basically like this, it's closed. So all these requests can't get through now. And so it has something called a half-open state. So think of an angle here where 1 out of every 10 transactions is allowed to go through. And what it does is reject, 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 let through. What's the response time? 23 seconds. Whoops, it's still bad. So stop, stop, stop. Let another one through. What's it now? 2 seconds. Okay, it's getting better. Now close. And so that's the best kind of circuit breaker. So it's important to know not only just, oh yeah, that tool has a circuit breaker, but what kind of circuit breaker is it between one of those three? Again, the real time is usually what's most common. But also the algorithms used within there. Some of them do leverage timeouts. Some of them also just leverage a trend analysis, which personally I think are much better.
Nice. That's good. So, I mean, the industry is moving because it's not reliable towards more asynchronous messages. So I know that asynchronous messages are a good thing to do. But what are your thoughts on, like, what are the trends going on in asynchronous messages, like to make the network more reliable, resilient, architecture?
Sure. Yeah. So I love this topic because when we talk about, so how do you make networks more reliable? Well, aside from the technical aspect of the actual physical equipment and stuff, one way we can make our systems more reliable, because the network is not, there will be network failures. Use of asynchronous communications is actually, Rohit, you hit the nail on the head. One technique for actually increasing the overall reliability of a business transaction. And now, while you may disagree with me, let me explain. Rohit may not, but others listening may say, no, that's the messaging is horribly unreliable. But hear me out, because if we're talking about a business transaction where, let me use a really simple example. I'm going to buy a book on, let's say, some sort of book website. Now, payment is not required for me to get my order ID and to actually order that book. So that happens, let's say, after the fact, or there's an option for that payment to happen after. So picture the scenario if I order the book and then I try to apply my credit card and that credit card service is down, or let's say the payment service is down, then I can't order that book. And so we talk about reliability in terms of saying, whoops, can't place that order because the payment system or the payment service is down. Use of asynchronous messaging allows me to do the following. I can place the order, insert the order into my order database, generate an order ID and give that to you. And say, here you go, you get an email saying, congratulations, your order is placed. And then asynchronously, because of unreliable aspects in the network and also a lot of the other fallacies we're going to talk about, and the point is if that payment service is down, I can do that later. I've got that in a persisted queue to be able to be processed when that service comes back up, or if it's having problems, wait a little bit, do some retries. The point is no one's waiting, like physically waiting to say, the system seems like it's down. So yeah, that's one scenario to actually improve the overall reliability of systems, knowing that the network is not reliable.
Now,
Then
in your scenario, like, you bought a stock and then now, saying, oh, I don't want to buy this stock. So, and the network is down. So, I mean, what are the pattern you're going to like? And I can think of like, compensation pattern, like just to see, to compensate based on the transaction which is already made. So what are things we can do?
Yeah. So, so within the kind of the distributed computing, when we talk about reliability, there's also the aspect of transactionality. And I, Rohit, am not a big fan of compensating frameworks in distributed architecture. I see them as well, quite frankly, not to flower it up, soften it up a bit. I see them as pure evil, quite frankly. You see, because as things happen in distributed computing, I may tell you to do something, and then I'll tell somebody else listening on this podcast to do something. But when you insert something, let's say a new account or initiate a transfer, other things happen. As a matter of fact, the data that you have now stored in your separately deployed unit of software in a distributed system, other types of systems may be starting to read and act on that data. So if I tell you to just go ahead and remove it, two things happen, Rohit. First, others may have taken action on that data that I'm now telling you to remove. And so now I've got inconsistencies throughout the system. But worse, number two, there are side effects to taking actions on inserting, updating, or deleting things that may have rolling effects that I'm not aware of. If I tell you, insert a new account for our customer, so I'm registering on the website, and you insert my profile information, and then another system is trying to insert my credit card information. And all of a sudden, that system's down or that service is down. And so, Rohit, I say to you, oh, can you delete that profile now? And so you do a compensating transaction, which instead of the insert is now a delete. And that rolls up to cause all sorts of clearing of preferences, which aren't there, so that crashes. And an email sent to me saying, so sorry to see you go. here's a 15% off coupon if you'll come back. And of course, I get this email and say, I haven't even registered yet. Why am I getting a 15% off coupon? And so it's inconsistency of data everywhere. However, and that's what's usually called, Rohit, in most distributed computing, a saga. I don't like the compensation framework aspect of sagas, but what I do really like is use of sagas leveraging finite state machines. So in other words, the owner of that information or the workflow, let's say, whether it be the owner of the information or the owner of the business process, which could be an orchestrator, actually has a finite state machine which stores the actual state of that particular order. So let's say I do an order and insert it. That order gets created. Now I try to apply a payment. Payment can't be applied. So instead of telling you to delete the order, I tell you the payment can't be applied and you change the state of that order. It's still inserted in your table, right? But I change the state of it to say payment rejected.
So basically what you're suggesting is that in the distributed system, we always should think about insert. Delete is also an insert. Everything is an insert as an event. So
Yes.
You can replay that event, no matter how that got replayed, get created on the other side whenever eventually it gets it.
Yeah, right? Precisely. Yeah.
Right.
And that way, the order stays there. You've inserted an order. It just has a certain state. Now, maybe the payment's rejected and somebody says, okay, I don't want it. Then that would be canceled. And then in that case, we know that it existed and was canceled. There's all sorts of stuff you could do, but it's very complicated. I'm not saying it's easy, but that's my preference with when we, kind of rolling back to this fallacy number one about things being reliable. Well, they're not. And one way to also manage those business transactions that do span multiple systems in cloud infrastructure is to leverage these state machines so that we know exactly at any point in time, A, what happened, good or bad, and what should happen next, and how do I take action on that? And so, what's so funny, Rohit, is you just mentioned about earlier about use of asynchronous communication events. And the interesting and fascinating thing is that most of the time when we try to create reliable systems using these state machines, usually, not always, but usually those are event-driven. In other words, when the state changes on that particular order, an event is usually fired off to do something else.
Yep.
Fill the order, notify the customer, reapply payment, and these are all events. And so, not surprisingly, async is really used a lot in sagas when we start talking about distributed transactions to address this issue that the network, in fact, is not reliable. Yeah.
Awesome. This is a great first of our talk, which is the fallacy of a distributed system. I look forward for our next fallacy in our next session.